Look at this. This gray, powdery material is literally one of the foundations of modern civilization. Look around you right now. Whether you're sitting inside a high-rise in Chicago, walking along a sidewalk in London, or driving across a bridge in Seattle, you're surrounded by the same quiet gray monopoly. Concrete. Did you know concrete is the second most consumed material on Earth, surpassed only by water? We use an astonishing amount of it. In just a few years, humanity can consume more concrete than was used across entire generations of modern construction. China alone poured more cement between 2011 and 2013 than the United States used throughout the entire 20th century. Think about what that means. Entire cities rising from empty land, highways stretching across continents, bridges, towers, dams, foundations, and sidewalks, all held together by the same gray, powdery binder. But what if this world-shaping material is actually a compromise? What if our dependence on Portland cement means we're building the future on rising carbon emissions, materials that eventually crack, and structures with weakness built into them from the beginning? Today on Survival Roots, we're exploring a quiet revolution already unfolding across America. Inside laboratories, research centers, and commercial pilot plants, innovators are rewriting the basic recipe of construction. They're developing materials that don't simply improve concrete. Some could challenge the need for conventional concrete altogether. We're talking about growing solid building materials with bacteria in a process inspired by coral reefs, turning loose sand into stone with a tiny electrical current, and creating new foundations and structural systems designed to last far longer than the materials we rely on today. If you're a builder, a homesteader, a DIY enthusiast, or simply someone who dreams about building a permanent, intelligent, environmentally friendly home without spending a fortune, this is a story worth paying attention to. So, are you ready to look beneath the gray surface and discover the materials that could redefine how we build? Let's get started. Section 1. The dirty secret and built-in fragility of Portland cement. To understand where construction may be heading, we first need to look carefully at what we're using today. And modern concrete has a dark secret. It begins with Portland cement. Invented in 1824 by a bricklayer named Joseph Aspdin in Leeds, England, Portland cement became the chemical glue that binds sand and gravel together to create concrete. The problem is the way we manufacture it. To produce Portland cement, limestone, made largely from calcium carbonate, is heated inside an enormous rotating kiln to around 1,450 degrees Celsius, nearly 2,600 degrees Fahrenheit. Reaching temperatures that extreme requires tremendous amounts of energy, traditionally supplied by burning coal, natural gas, or other fuels. But the fuel is only part of the problem. The bigger issue happens inside the limestone itself through a chemical reaction known as calcination. At extreme temperatures, calcium carbonate breaks apart. The process creates calcium oxide, the lime needed for cement production, but it also releases carbon dioxide. That means even if every cement kiln in the world somehow ran entirely on clean, renewable electricity, the chemical reaction inside the stone would still release enormous amounts of CO2. The emissions are built directly into the recipe. The world produces roughly 4 billion metric tons of cement every year, and conventional production releases enormous quantities of carbon dioxide along the way. Cement manufacturing alone is responsible for a significant share of global greenhouse gas emissions. But carbon isn't the only problem. Modern concrete is also surprisingly fragile over long periods of time. Think about ancient Roman structures, like the Pantheon in Rome. Its enormous concrete dome has remained standing for more than 1,900 years without steel reinforcement. Now compare that with many modern bridges, sidewalks, parking structures, and concrete walls that begin showing cracks, surface damage, and deterioration within decades. Why does this happen? Modern reinforced concrete depends heavily on steel rebar to handle tensile forces. Concrete itself performs extremely well under compression, but steel provides the strength needed where the structure is being pulled or bent. The problem is that concrete is naturally porous. Over time, moisture, salt, and air can move through microscopic pores and cracks until they reach the steel reinforcement buried inside. Then the steel begins to rust. As rust forms, the steel expands. That expansion pushes outward against the surrounding concrete until cracks develop, pieces break away, and the structure slowly begins damaging itself from the inside. We spend enormous amounts of money repairing bridges, roads, walls, foundations, and other concrete structures because of this cycle. Think about how strange that is. We have built much of the modern world with a material that can begin its long process of deterioration not long after it has finished curing. But what if we could bypass the extreme heat, avoid the limestone problem, and even reduce some of this built-in fragility? What if instead of forcing materials into shape with fire, we learn to build more like nature does? Section 2. Growing concrete like coral. Biomason's Bacterial Revolution. Our first stop takes us to Research Triangle Park in North Carolina, where a company called Biomason has been working on something that sounds almost like science fiction. Biomason was founded in 2012 by architect and scientist Ginger Krieg Dossier. And the idea behind the company is remarkably simple to describe, even if the science behind it is anything but ordinary. They grow building material. Dossier looked toward the ocean and noticed something fascinating about coral reefs. Coral can form massive mineral structures capable of surviving powerful waves and constant exposure to salt water. Yet those structures aren't produced inside giant industrial kilns. Nature builds them through biology. That idea helped inspire a process known as microbially induced calcite precipitation, or MICP. Instead of beginning with cement powder, the process starts with aggregates such as sand or recycled construction material. Then a naturally occurring bacterium called Sporosarcina pasteurei is introduced, along with a nutrient solution containing calcium ions and urea. These microscopic organisms begin doing the work. As the bacteria metabolize their nutrients, they produce an enzyme called urease. That enzyme triggers a chemical reaction that converts urea into carbonate ions. Those carbonate ions then react with calcium in the surrounding solution. The result is calcium carbonate. That's the same basic mineral found in limestone, clamshells, and oyster shells. As the calcium carbonate forms, tiny mineral crystals begin appearing between individual grains of sand. Those crystals continue growing until they bridge the spaces between the particles, gradually locking everything together. Loose sand becomes a solid structural material. And perhaps the most remarkable part is that the process occurs at room temperature. No giant kiln, no extreme heat, no need to burn limestone at nearly 1500 degrees Celsius. Biomason has moved this technology beyond small laboratory experiments. Through its C-Crete technology, the company developed bio-based materials, including mimic tiles, which have been installed in commercial spaces in Europe, including retail environments associated with companies such as H&M. Biomason also partnered with IBF, a major precast concrete producer in Denmark, to establish a commercial biobeton manufacturing operation in Ikast. The facility was designed to produce thousands of square meters of bio-based tile each year. According to the original claims surrounding the technology, these bio-based materials can be lighter than conventional concrete while delivering impressive strength. There's another interesting advantage. Traditional cement creates the familiar gray appearance we associate with concrete. But a calcium carbonate binder can allow more of the natural appearance of the original sand and stone to remain visible. The material can retain the colors and texture of the aggregates themselves. Now imagine building walls where the binding material wasn't created inside a roaring industrial kiln, but was instead grown by microscopic organisms over a matter of hours. Instead of waiting weeks for conventional concrete to reach its full curing strength, biology would be doing the work. That's a very different way of thinking about construction. And for survival routes, That's exactly where things start becoming interesting. Section 3. Squeezing sand with electricity. The seawater breakthrough. If growing building material with bacteria sounds unbelievable, the next technology pushes the idea even further. Researchers at Northwestern University, led by Associate Professor Alessandro Rota-Loria, developed a method for turning ordinary marine sand into solid material using seawater and a small electrical current. In other words, loose sand can begin behaving more like stone, and the electrical voltage required is remarkably low. The process works by placing electrodes into sand saturated with seawater and applying a small electrical voltage. At the negative electrode, the electrical reaction changes the chemistry of the surrounding water. Water molecules are split, producing hydroxide ions and locally increasing the pH. Meanwhile, carbon dioxide is introduced into the water, helping create bicarbonate ions. Seawater already contains dissolved minerals, including calcium and magnesium. Once the electrical reaction changes the local chemical environment, some of those dissolved minerals begin coming out of solution. They precipitate into solid minerals, such as calcium carbonate and magnesium hydroxide. Those minerals begin forming around the loose grains of sand. Over time, the growing mineral crystals act like tiny bridges between individual particles. Instead of thousands of grains sliding freely past each other, they become locked together inside a solid mineral matrix. Loose marine sand gradually becomes a cohesive, rock-like material. But the idea becomes even more interesting when carbon enters the equation. The process can incorporate carbon dioxide into the resulting mineral structure. Instead of merely attempting to reduce carbon emissions during construction, the material itself can store CO2 within the minerals created during the process. That creates an entirely different possibility. Rather than hauling enormous quantities of concrete to a coastline, imagine using the sand and seawater already present at the site. Coastal erosion is an enormous challenge around the world. Large portions of sandy shorelines are threatened by erosion, while huge populations live within coastal regions. Traditionally, one response has been to construct massive concrete seawalls and other heavy coastal barriers. But the Northwestern concept suggests another possibility. Electrodes could potentially be installed directly into coastal sand. A small electrical current, potentially powered by solar energy, could then trigger mineral formation beneath the surface. Instead of transporting huge amounts of material to the shoreline, protective stone-like structures could potentially be formed directly where they are needed. And the proposed economics make the idea even more interesting. The process has been discussed as potentially costing only a few dollars per cubic meter under certain conditions, compared with much higher costs associated with conventional binders. Then comes another unusual feature. If the structure eventually needed to be removed, reversing the electrochemical conditions could potentially weaken or reverse the mineral bonding process. The solidified material could return toward loose sand instead of requiring the kind of heavy demolition associated with conventional concrete. Think about that for a moment. Infrastructure that can be formed directly from the ground beneath your feet, strengthened when needed, and potentially reversed later. Instead of treating the coastline as something we must cover with imported concrete, we could work with minerals already dissolved in the surrounding seawater. Sometimes the raw materials for a solution may already be sitting right in front of us. Section 4. The Cold Chemistry. Sublime Systems Electro-Cement. Now let's leave the shoreline and move into a very different kind of construction revolution. Sublime Systems is approaching the cement problem through industrial electrochemistry. The company emerged from research connected to MIT and was co-founded by Dr. Leah Ellis and Dr. Yetming Chiang, a scientist known for his work in electrochemistry and advanced battery technology. Sublime recognized something important about construction. The cement industry is conservative for a reason. When engineers are designing bridges, foundations, towers, and 50-story buildings, they don't necessarily want a completely unfamiliar material with entirely new performance rules. They want something they already understand. Builders understand cement. Engineers understand cement. Ready-mix companies already have equipment designed around cement. Construction codes are built around known cement performance. So Sublime asked a very practical question. What if we could produce something that works like the cement the industry already trusts, but change the chemistry used to make it? Their answer is an electrochemical cement manufacturing process. Instead of heating limestone inside a massive fossil-fueled kiln at roughly 1,450 degrees Celsius, Sublime uses electricity to extract reactive calcium and silicate materials from alternative mineral sources and industrial material streams. The important difference is the pathway. Traditional Portland cement production relies on extreme heat. Sublime attempts to replace that thermal process with electrochemistry. Because the extraction and separation processes operate without the conventional high-temperature kiln route, the system can avoid much of the fossil fuel combustion normally associated with cement production. And when the electricity comes from renewable sources such as wind or solar, the manufacturing process can dramatically reduce carbon emissions. But here's what makes the approach especially important commercially. The final material is intended to function as a direct replacement for conventional cement. That means concrete producers don't necessarily need completely new mixing systems. Engineers don't have to abandon everything they understand about structural concrete. Construction workers don't need an entirely new building technique. The goal is simple: make a familiar product using radically different chemistry. And Sublime isn't treating this as a distant laboratory concept. The company has attracted major investment and moved its material into real-world pilot projects. Large technology companies, including Microsoft and Stack Infrastructure, have worked with Sublime around the use of low-carbon concrete in major facilities such as data centers. That's what makes this approach so interesting. Sometimes replacing an enormous global industry doesn't require changing everything the customer uses. Sometimes the smarter approach is to leave the final product familiar and completely reinvent how that product is manufactured. Section 5. The Rock Refinery. Brimstone's carbon-negative on-spec formula. While Sublime Systems attacks the problem through electrochemistry, another American company is approaching cement from a geological direction. That company is Brimstone, based in Oakland, California, and founded by Dr. Cody Finke. The basic idea begins with a simple question. If limestone creates carbon dioxide when it is processed into cement, why use limestone at all? Calcium exists in many other rocks. Finke looked toward calcium-bearing silicate rocks, including materials related to basalt. Silicate minerals are extraordinarily abundant across the Earth's crust, and unlike carbonate rock, such as limestone, they don't contain the same built-in carbon dioxide that is released during calcination. That creates an entirely different path to cement. Brimstone doesn't describe its operation as merely a cement plant. It describes the concept as a rock refinery. The process begins with calcium-bearing silicate rock. The rock is crushed and pulverized into smaller particles. Then comes a hydrometallurgical stage, in which chemical processing separates useful components, including calcium and aluminum. The silica remaining from the process can then be processed into a supplementary cementitious material, or SCM. Meanwhile, the extracted calcium compounds can be used to produce clinker, which is then combined with gypsum and milled into Portland cement. The crucial difference is where the calcium came from. In conventional cement manufacturing, the calcium comes from limestone. When limestone is heated, carbon dioxide is chemically released from the rock. Brimstone, instead, gets its calcium from silicate rock. Because the source isn't carbonate-based limestone, the rock itself doesn't release that same stream of CO2 during clinker production. The result is intended to be ordinary Portland cement, produced through a very different mineral pathway, and this is where Brimstone's strategy becomes especially interesting. The company isn't trying to produce only cement. A traditional cement plant generally focuses on one primary product. Brimstone's rock refinery model is designed to create several valuable materials from the same raw rock. The process can produce Portland cement. It can produce supplementary cementitious material. And it can produce alumina, the major industrial feedstock used to manufacture aluminum. Instead of taking one rock, extracting one product, and leaving behind large amounts of unwanted material, the strategy attempts to turn more of the original mineral into something commercially valuable. That's where the economics become central to the idea. If several valuable products come from the same processing facility, revenue doesn't have to depend entirely on cement. The value of SCM and alumina can help support the economics of the overall process. Brimstone believes that this multi-product model could allow its cement to compete directly with conventional high-carbon cement on price. The concept has attracted major financial backing, including investment connected to Breakthrough Energy Ventures and the Amazon Climate Pledge Fund. The company has also received major federal support from the U.S. Department of Energy toward development of a commercial-scale facility capable of producing large quantities of lower-carbon cement. It's an important lesson. A cleaner construction material doesn't necessarily have to survive by asking customers to pay more simply because it's better for the environment. If you redesign the entire production system intelligently, sustainability and economics can potentially work together. And in Brimstone's case, that redesign begins with something as basic as choosing a different rock. Section 6. Painting with Mountains. C-Crete's naturally colored, cement-free concrete. If you want to see what happens when alternative cement chemistry leaves the laboratory and arrives on an actual construction site, C-Crete Technologies offers one of the most interesting examples. C-Crete was founded in San Leandro, California, by MIT PhD graduate Dr. Ruzbe Savari. The company developed a proprietary binder that eliminates conventional Portland cement clinker from the concrete mix. Instead of depending on the traditional limestone clinker pathway, C-Crete can work with abundant mineral sources, such as granite, basalt, and zeolite, as well as industrial materials such as slag. The objective is straightforward. Create a binder capable of replacing Portland cement without requiring the conventional cement manufacturing process. And C-Crete has already moved beyond theory. The company has published independently verified environmental product declarations showing a dramatically lower carbon footprint than conventional Portland cement. Its clinker-free binder has been reported with a global warming potential far below the typical U.S. industry average. At the same time, the material has demonstrated compressive strengths suitable for demanding structural applications. That combination matters. Low emissions are useful, but builders still need strength. Engineers still need predictable performance. Developers still need material they can actually pour. C-Crete is attempting to deliver all three. But there's another feature that may be especially interesting to architects, homeowners, and DIY builders. Color. Traditional Portland cement gives concrete its familiar gray appearance. C-Crete's binder doesn't rely on the same conventional clinker, so the natural mineral character of the raw materials can remain visible in the finished concrete. A basalt-based mix can create a rich, dark volcanic appearance. Zeolite can produce a different natural tone. Granite can create a speckled stone-like finish. And those colors come from the mineral feedstock itself, rather than from adding artificial pigments afterward. It's almost like building with the natural color palette of the mountain. But appearance alone wouldn't make this important. The biggest milestone is that C-Crete's material has already been used in commercial construction. In Manhattan, the company completed a major pour associated with the new headquarters at 270 Park Avenue. The project brought granite-based, cement-free concrete into a significant structural application in the middle of New York City. C-Crete has also completed basalt-based concrete pours in Seattle and other projects across the United States. Thousands of tons of its material have already been placed in real-world conditions. That makes this technology different from something that exists only inside a research paper or laboratory mold. Concrete trucks have carried it, workers have poured it, buildings are using it, and the company has positioned its binders to compete economically with conventional cement, rather than requiring customers to accept a large environmental premium. Strong, visually distinctive, lower in carbon, and already entering commercial construction. That is what the transition from experiment to building material actually looks like. Section 7. The Rust Eater. Ferrock's saltwater superpower. Now let's bring this revolution closer to the workshop. If you're a homesteader, prepper, or DIY builder who loves the idea of turning waste into something useful, Ferrock is one of the most fascinating materials in this entire story. Ferrock was discovered accidentally by researcher Dr. David Stone while working at the University of Arizona. Stone was exploring ways of dealing with iron and corrosion when he encountered a chemical reaction that could create an extremely strong building material. And the ingredients are surprisingly familiar. Ferrock is made largely from recycled materials. One major ingredient is waste steel dust, a fine iron-rich powder produced by steel manufacturing and other industrial processes. Much of this material would otherwise be treated as waste. Another ingredient is finely ground recycled glass, which provides silica. Combine the steel dust and silica with water, then expose the mixture to carbon dioxide, and the chemistry begins changing. The iron doesn't simply rust in the ordinary way. It reacts in a process that creates a dense iron carbonate-based matrix. As that matrix develops, carbon dioxide becomes locked into the hardened material. According to the claims surrounding Ferrock, the material can absorb more carbon dioxide during curing than is released during its production. That makes the concept not simply lower carbon, but carbon negative. But Ferrock has another unusual characteristic: saltwater. Remember one of the biggest problems with traditional reinforced concrete? Saltwater can penetrate the concrete and accelerate corrosion of the steel reinforcement hidden inside. The rust expands. The concrete cracks. The structure weakens. Ferrock turns that familiar problem on its head. Its chemistry is already built around iron and carbonation. Instead of saltwater automatically becoming an enemy, exposure to marine conditions can support reactions that make the material increasingly dense and hard. That makes Ferrock especially interesting for coastal construction, marine structures, foundations, pipes, tanks, and other applications where conventional steel-reinforced concrete often struggles with corrosion. And from the perspective of an off-grid builder, there's something deeply appealing about the philosophy behind it. Instead of asking how we can completely prevent natural reactions, such as rust, Ferrock asks whether those reactions can become part of the building system itself. Take waste steel dust, take recycled glass, use carbon dioxide as part of the curing process. And instead of producing another disposable waste stream, turn those materials into something structural. The idea is almost the perfect expression of the survival roots mindset. Don't automatically fight the chemistry around you. Understand it. Then design the material so the chemistry works for you. Section 8. Bypassing the pore. Ground screws and steel honeycombs. But what if the smartest replacement for concrete isn't another type of concrete at all? What if the best solution is simply not to pour it? As homesteaders, off-grid builders, and DIY enthusiasts, it's easy to assume that every permanent structure needs to begin the same way. Excavate the ground, dig trenches or holes, build forms, bring in cement, mix concrete, pour it, wait for it to cure, then finally begin building the structure above it. That process can mean heavy machinery, disturbed soil, mud, labor, material costs, and days of waiting. But there's another approach that has been quietly spreading through the construction world: ground screws. Also known as helical piles in related foundation systems, ground screws are essentially enormous, heavy-duty steel screws installed directly into the soil. Instead of excavating a large footing and filling it with concrete, the steel foundation element is driven or screwed into the ground using handheld or light hydraulic equipment. The engineered threads grip and interact with the surrounding soil as the screw moves downward. Once installed, the ground screw provides a stable support point for the structure above. And the installation can happen remarkably quickly. No large concrete pour, no long curing period, no giant excavation. For the right project, a cabin, greenhouse, deck, or other lightweight structure can be supported by a series of ground screws installed within a single day. Once the screws are positioned and leveled, the framing above them can begin almost immediately. There's also the question of cost. When you include excavation labor, formwork, cement, mixing, equipment, and waiting time, a ground screw foundation can become economically attractive for certain projects. Then there is reversibility. Concrete foundations are permanent in a very literal sense. Removing them usually means breaking them apart and hauling away heavy rubble. Ground screws can be removed. If a structure needs to move, the screws can potentially be unscrewed from the soil and reused elsewhere. Instead of leaving a mass of broken concrete underground, the land can be returned much closer to its original condition. But this idea of bypassing concrete doesn't stop with cabins and decks. Scale it up dramatically, and you arrive at systems such as B-Core, developed by China's Broad Group. After the devastating Sichuan earthquake in 2008, where enormous numbers of people died beneath collapsed structures, Broad Group pursued alternatives to heavy conventional construction. One result was B-Core. The system uses two thin steel plates separated by a dense internal lattice of hollow steel tubes. The result resembles an enormous structural steel honeycomb. Because much of the interior volume is empty, the panel can be dramatically lighter than a solid concrete slab of similar dimensions. Yet the internal lattice gives it considerable strength and flexibility. The design was developed with extreme structural resilience in mind, including resistance to major earthquakes. And because the panels can be manufactured in controlled factory conditions, entire sections of a building can be prefabricated before they ever arrive at the construction site. Once delivered, the components can be assembled using mechanical connections such as bolts. That changes the entire construction process. Instead of spending months forming, reinforcing, pouring, and curing floor after floor of concrete, large building components can arrive ready for assembly. Broad Group has demonstrated extremely rapid multi-story construction using prefabricated systems of this type. So whether you're building a small cabin in the forest with ground screws or imagining an entire city assembled from lightweight steel structural panels, the principle is the same. Maybe replacing concrete doesn't always mean inventing a better binder. Sometimes it means asking whether the concrete pour was necessary in the first place. And when it isn't, removing that step can mean greater speed, lower weight, less disturbance, easier disassembly, and a completely different approach to resilience. Laying your survival roots. We've covered a lot of ground. We've gone from the microscopic world where bacteria grow mineral binders between grains of sand, to coastlines where tiny electrical currents can transform loose marine sediment into stone-like material. We've looked at electrochemical cement, rock refineries, naturally colored cement-free binders, recycled iron-based materials, ground screws, and lightweight steel honeycomb structures. But beneath all of these technologies is the same larger idea. Building doesn't always have to mean using more heat, more fuel, more weight, and more brute force to make nature behave the way we want. Sometimes the smarter path begins with understanding the chemistry, biology, geology, and physics already operating around us. Then we learn how to work with those systems. The gray monopoly of Portland cement is beginning to crack. The inventions we've explored show that the future of construction could be stronger, more flexible, more beautiful, more affordable, and far more closely connected to the materials and natural processes already surrounding us. And that's what Survival Roots is really about. Building deep, resilient roots, creating structures that last, protecting the land we depend on, and becoming smarter and more self-sufficient in the way we build. So here's the question I want to leave with you. If you were starting your dream home tomorrow, which of these technologies would you choose? Would you grow your walls with Biomason's bacteria? Would you use electricity to transform sand into stone? Would you build with mineral-based cement alternatives? Or would you skip the concrete pour entirely and place your home on ground screws? Let me know in the comments below. I read every one of them. And if you enjoyed this video and learned something new, hit the like button, subscribe to Survival Roots, and share this with another builder, homesteader, or DIY enthusiast. Together, we can build a stronger, smarter, and greener future. Thank you for watching. Stay curious, stay resilient, and I'll see you in the next adventure.